everyone. Welcome into lecture number 15 of differential equations. This lecture is our first part of our study of power series solutions to differential equations. In the last lecture, we reviewed power series in general, and now we're going to try to find power series solutions to certain kinds of differential equations. And the kinds of differential equations that we're going to study are going to be linear, homogeneous, second-order equations. So for this lecture and for the next lecture, we will study the following differential equations. So we'll study linear, homogeneous, second-order differential equations of the form. And so we'll write this, I'm going to label this equation because this is going to be our go-to equation, but p of x y double prime plus q of x times y prime plus function r of x times y equals 0. And again, this is just a linear, homogeneous, second-order equation, so there's nothing new here. But this is going to be what we're going to call equation 1 star. And before we get into solving these equations, we need a couple of definitions. So here's what we'll say. A point x naught is said to be an ordinary point of this equation. So an ordinary point of this equation star if and only if a couple things are true. One is that p of x naught is not equal to 0. So if p of x naught is not 0, that means that obviously we can divide through by p of x, at least near this point, right? So p of x naught is not equal to 0. Let's just leave it at that for now. We'll return to this definition a little later in this lecture of ordinary point, and we'll add some criteria to this. But for now, this is good enough that that p of x naught is not equal to 0. That's going to be enough for us to call this an ordinary point. And if p of x naught is equal to 0, then we're going to say that x naught is a singular point. So if p of x naught, p again is the leading coefficient function here, right? So if this is equal to 0, then x naught is a singular point of the differential equation. And we'll talk about what to do with singular points in our next lecture, or in a future lecture at least. So this is a singular point of star. Okay, so we are going to, for this lecture, study how to solve, or how to try to find, power series solutions to this equation star near an ordinary point, so centered at an ordinary point. So that's our goal for this lecture. We seek to find a power series solution. So PS here is power series solution to equation star centered at an ordinary point. Again, for this lecture, centered at an ordinary point x naught. And so our solution is going to be of the form of a power series. And once I write this down, then we'll talk about what exactly needs to be determined in finding the solution. So I'm going to call the solution phi. Usually phi is what we call the solution after we know it, but I'm just going to call it phi to start here. So it's going to be a power series. So it's a sum, n goes from 0 to infinity, a sub n times x minus x naught to the power n. So this is just a general power series. And again, we're saying that x naught in this scenario is an ordinary point, right? So we're going to try to solve this where x naught's an ordinary point. And let's think about what actually needs to be determined here. So if we've chosen a center point, then we know x naught. X naught is not unknown. X is a variable and n is an index. So the only unknowns here, I say the only unknowns, there are infinitely many of them, but the only unknowns are the coefficients, a sub n, right? So the goal here, or the job here, I'll say the goal, but the job here is to determine the coefficient sequence. So we need to determine the coefficients of the solution function. So we need to know a sub n, right? For all n, or at least as many as we can possibly find. So what I'm going to do here is I'm going to start with an example that we can solve other ways, just so we can see how this works. So a very simple equation. So this is like a motivational equation. All right, so I would like to try to solve, this is what we're going to do together, solve this differential equation, y double prime plus y equals 0, centered at, or I'm going to say near, x naught equals 0. So I want to try to solve this differential equation using power series methods. So in other words, try to find a power series solution to this differential equation centered at the origin, centered at 0. All right, the coefficient functions here are very, very simple, right? That's what I was saying. P of x is equal to 1, Q of x is equal to 0, and R of x is equal to 1. They're just constants, all right? So this is going to be a very straightforward example, hopefully. So what we're going to do is we are going to start off by writing down the power series in general. So we're going to say, all right, we want our y to be of this form, right? We want our y to be a power series and goes from 0 to infinity, a sub n, x minus 0 in this case, to the power n. So obviously that's just going to be, I'll write out exactly what it is. This is just going to be a sub n, x to the power n, right? And then we need to take the derivatives. We did this in a previous lecture, so I'm going to quickly remind us how this works. But the derivative of a power series does a couple things. The power comes down just like a polynomial, but then it shifts the index for this general power series, right? So the first derivative is sum. N goes from 1 to infinity of n a sub n x to the n minus 1, right? And that means that the second derivative is going to be y double prime. It's going to be the sum n starting at 2 to infinity of n times n minus 1 a sub n x to the n minus 2. And I hope you remember from that previous lecture that we talked about we're going to want to shift these. So in general, you can leave these as they are and plug them into the differential equation now. So let's do it that way, actually. Let's just plug these into the differential equation. Then we'll talk about shifting them. But this is what we're going to plug in for y double prime. And this series right here, we're going to plug in for y. We don't need y prime for this equation, but many times we will, right? So when we plug these in, the equation now becomes the sum, n starts at 2 to infinity, n minus 1, a sub n, x to the n minus 2. And we're going to add to that the next power series, sum n from 0 to infinity, a sub n, x to the n. And this is all supposed to add up to 0, right? Because this is a homogeneous differential equation. Okay, now what we would like to do is we need to solve for these coefficients, right? So what we would like to do is combine this into a single sum and then think about what must be true of the coefficients for that single sum to add up to 0. All right, and remember this is a power series function, so I'll return to that in a moment. But to be able to do that, what we need to do is we need to have the same powers of x, all right, among other things, but that's the first thing that we need. We need to make sure that we have the same powers of x. So we need to make sure that those powers are the same. This one is already starting at 0. It's already just n. So the first one here, the index of the second derivative is the one that we want to shift. And this is where I was saying in the previous lecture, we talked about how to do this. If we want to add 2 to all the n's in the sum and, what's inside the sum, then we need to reduce the index by 2 in the sum itself, right? We need to start at 2 less if we're adding 2 here. So we can do that. It turns out that it becomes, and again, this is what you're hopefully practiced in the last lecture, but it becomes the sum n goes from 0 to infinity. All these n's are going to be increased by 2. So it's going to be now n plus 2 times n plus 1, a sub n plus 2, x to the n, right? And then this one is going to be the sum, n goes from 0 to infinity, a sub n, x to the n equals 0. And at this point, sometimes what will happen is that you'll have now the powers of x being the same, so they'll both be x to the n, but sometimes your sums will start at different starting values in the index. In this case, they don't. They will start at 0. So everything here is the same, right? And when I say everything, what I mean is we have the sum ends, the sums themselves start at the same value, and then also the powers of x are the same. And so we can kind of combine these, right? Factor them in some sense. And we can write this then as a single sum, n goes from 0 to infinity, of the new coefficients are going to be n plus 2 times n plus 1, a sub n plus 2 plus a sub n, and then we can factor this x sub n. That's a common term, right? And there we go. Now we have a single sum that's supposed to add up to 0. So this is kind of the goal of the first part of our solution here. So we've written this out. We've plugged in our power series into our differential equation. We've shifted the index as needed, right? First to get the powers of n the same, and then we made sure that the starting values in the sum and are the same, and the index are the same. And then we combine it into a single sum. And so now we ask ourselves, how is it possible that this single power series, right, is equal to 0? Well, and by the way, this is where we remember that this is a function of x, right? And it's got to be defined at least at x equals 0, but, you know, in a neighborhood of x equals 0 is what we're looking for. So we need this as a function to equal 0 for all x. And the only way that that can happen is for the coefficients to all be equal to 0, right? So the only way that this sum can equal 0 for all x, at least in some interval, is for these coefficients to each equal 0. All right, and so we set this coefficient here, we set this equal to 0, and we are going to try to solve for the a values that we get from this. This right here, this equation where we've set the coefficients equal to 0, this is very important. It gets a name. This is called the recurrence relation of the power series solution. So the recurrence relation. I'm going to probably denote that just by RR as we move forward. But setting this equal to 0, that gives us the recurrence relation. And the reason it's called a recurrence relation is because now what we can do is we can write a formula to solve for the a n plus 2 term in terms of the a sub n term. All right, so now we can solve for the highest indexed term, right? So in this case, it's a n plus 2. And so what it's going to be is that a sub n plus 2 is going to be equal to, we move this over, divide by these terms, right? So it's going to be negative 1, negative because we move it over n plus 2 times n plus 1, all times a sub n. Okay? All right, so what does this mean? Well, this means that every term is related to the term that comes 2 after it, right? And we need some kind of starting point here of where to start thinking about these, and then we can make a table basically. But basically, what we're going to have, let's just break it up this way. Let's say we have our evens and our odds. Let's start with the evens, right? So we'll consider 0 to be an even. So we'll say, all right, when n is equal to 0, what do we have? Well, we just have a sub 0. There's nothing we can say about that, right? We just have a sub 0. Go to the next one. When n equals 2, what do we have? Well, if n, maybe I shouldn't be calling this n equals 2. Let's do it this way. I'm going to call it k. All right, k equals 2. Then a sub 2, if that's k, right, then this is going to be equal to negative 1 over, if k is 2, that's all of this. I'm going to just change this all. Sorry. I know you're probably, I'm going to swap out this for k, and then this one right here is going to become k minus 1, right? So just to shift this a little bit, and obviously that's going to change too. So another way to write this is that we have a sub k. So I want the index to be, the one that I'm working with, to be the one that's on this side. So a sub k is going to be negative 1 over k times k minus 1, and then all times a sub k minus 2. So the previous one. So I'm going to look at this formula right here. It's the same, right? I just swapped out k equals n plus 2 and then shifted accordingly, right? All right, so now if this is 2, now I can see exactly what's going to happen here, right? Because this will be 2 times 1. In my mind, I am very simple-minded, right? So that's 2 times 1, and if k is 2, then this is a sub 0. So now we have our a sub 2 in terms of a sub 0. I'm going to leave it the way it is and go to the next one. So we go to the next even one, right? We know that these are related by every 2. So the next one we go to 4, k equals 4. Well, then a sub 4 is going to equal what? It's going to equal negative 1 over 4 times 3 times a sub 2. All right? But look at this. We know what a sub 2 is in terms of a sub 1. So we can make that substitution, right? And we can write this as, okay, well, this is going to be negative 1 over 4 times 3 times this, right? So times negative 1 over 2 times 1 times a sub 0. And if we put this all together, we get that this is going to be negative 1 squared over 4 factorial times a sub 0, right? And this one up here is negative 1 to the 1 over 2 factorial a sub 0. We'll go to the next one. We're trying to notice a pattern here if possible. So maybe we've already noticed it, but let's do at least one more, right? So a sub 6, again, using our formula, is going to be negative 1 over 6 times 5 times a sub 4, right? Same deal. Plug in what we know up here, right? When we do so, we get negative 1 times negative 1 squared over 6 times 5 times 4 factorial a sub 0. And of course, that is negative 1 to the third power, right? Negative 1 cubed over 6 factorial a sub 0. Okay, and now we can make a guess. These are even, right? So let's say, all right, if our k is equal to 2 times n, so if our k is even, that's how we make this even, right? Then what do we know? Well, then our a sub 2n, or a sub k, is going to be equal to, just by our formula here, just look what we have. It's going to be negative 1 to the n, right? Negative 1 to the n over 2 times n factorial. That's exactly what's down below. 2n factorial times a sub 0. Okay, and so those are the coefficients on the even terms. That's the coefficients on the even terms. So what do we get? So for the even part of our solution, the even terms of our solution, we get, this is just part of our solution, right? So part of the solution. This is the even part. What we're going to get, we'll call it y1. We'll just call it y. I was going to say y sub e, but then we'll have y sub o, and we'll just call this y sub 1. So y sub 1, this part is, it's the sum of just the even terms, right? So it's going to be the sum as n goes from 0 to infinity, and we've got this all worked out. What we need to remember is that because we have only the even term right here, that's going to mean that we only get the even powers of x back here, right, in our solution. So that's the only thing that we need to be careful of at this point. But we've got our terms here. So I'm going to write it this way: a sub 2n x to the 2n, right? But then we know exactly what these are. So then these become the sum, n from 0 to infinity, negative 1 to the n over 2n factorial times a sub 0. So we can actually, that's a constant, right? So I'm going to write it up here. And then all times x to the 2n. That a sub 0 actually, since it's a constant, can be factored all the way out. And we can write this as y sub 1 equals a sub 0 times the sum, n goes from 0 to infinity, negative 1 to the n over 2n parentheses factorial times x to the 2n. Okay? And this is a power series, and hopefully you recognize what power series this is, right? What power series is this? Yeah, this is the power series for cosine, right? So this, just by working out our power series method here, we found that one of our solutions is a0 times cosine of x, right? Times cosine of x. All right, I'm not going to work through all the details of the odds because it's exactly the same process, except you start with k equal 1 and you plug into this same formula. So for the odds, here's what you're going to do. You're going to start with k equals 1, and then your first term is a1. There's nothing you can say about that, right? So this one is actually a free coefficient, right? And notice that up here the same thing happened. We had a0. The first one was free. Then the next one is k equals 3. So for k equals 3, what do we get? Well, a3 is going to be equal to negative 1. It's the same formula, right? Same formula. We're just plugging in odds. So it's going to be negative 1 over 3 times 2 times a1. All right? The next one, k equals 5, is going to be a sub 5 equals negative 1 squared over 5 times 4 times 3 times 2. There's not a 1 here, but you can put it, right? It's not going to, multiplying by 1 doesn't change anything. So this is going to be 5 factorial a sub 1 when you put it all together. And then if you get down to k equals 2n plus 1, so odd, right? You're going to find, and again, if you need to, and I recommend, pause the video here, just work this out and make sure you agree with everything I'm writing here. But a sub 2k plus 1 is going to be negative 1 to the n. I said 2k plus 1. It's 2n plus 1. All right, a sub 2n plus 1 is negative 1 to the n over 2n plus 1 factorial a sub 1. And so what you get from this one is that your second solution, y2, is going to be, same deal. I'm not going to go through all the work again, but it's going to be the odds, right? It's going to be a sub 1 times the sum, n goes from 0 to infinity, negative 1 to the n over odd 2n plus 1 factorial. And if we have only the odd terms, then we get only the odd powers, right? Only the odd coefficients means only the odd powers. So this will be x to the 2n plus 1. And of course, if we remembered that this one is cosine, we will also remember that the odd ones are sine, right? Alternating odd terms. This is going to be a1 times sine of x. And so altogether, our solution, so the total solution is going to be y of x equals a0 cosine of x plus a1 sine of x, where these a0 and a1 are arbitrary constants. So in other words, they're the free variables, right? They're the C1 and the C2 that we got using our other methods before. But at this point, you should check, again, that this is the same solution. So we just got this using power series, right? But this is the same solution that you would get if you went and back to this original equation and you use the characteristic equation method, characteristic polynomial method, right? So r squared plus 1 equals 0. You get two roots. They're plus or minus I. You plug into the formula for those, and you get the exact same solution, which you better, right? You better get the same solution, or at least an equivalent solution. In this case, it's the exact same solution using our power series method that we would have gotten from our characteristic polynomial method. But hopefully this example, as simple as it is, illustrates the process of how we want to use our power series and what we have to do to find our power series solutions, right? We have to, I'm going to write this all down in a moment, but basically we take the derivatives, we plug them into the differential equation, we combine it into one power series equation, right? One series equation, if possible, you know, and we'll see examples as we move forward where you maybe have a couple terms that are outside the sum, but then you set all those equal to 0 to get your recurrence relation. In this case, we have just one formula for all n, right? And then you solve for the next terms, the higher index terms, in terms of the lower ones, right? And shift the index if you need to. So if you think this is easier, like I do, it's a little more simple-minded, where you have the coefficient that you want on the left, right? And then you can write everything in terms of that on the right. Then you do that, and then you try to notice a pattern. Noticing the pattern is going to be probably the hardest part. So there will frequently be times when we just try to find, say, the first 4 or 5 terms of each power series solution by doing this process that we did right here, right? Plugging into the recurrence relation and finding the first 4 or 5 terms, and then we'll say that's good enough. We'll leave it at that for that problem. But it will say that in the instructions, okay? So let's now write down a summary of the process, and then we'll do an example, another example. So summary of the power series method. Okay, so number 1, and this is just exactly what I just went through, but I'm going to write it down so that we have it documented, right? But number 1 is to plug the power series into the differential equation. So this involves taking the derivatives or remembering. They're always going to be the same, right? Because this is just a generic power series. We take the derivative. These are always going to be the derivatives when you're centered at 0. It's going to be these same formulas. Plug them into the differential equation, okay? Number 2 then is to shift the indices if necessary. So if it's necessary to do so, you shift the indices and then combine into one sum. So you combine the entire equation into one sum. Maybe there's going to be some terms that are outside the sum. That's okay. But the rest of it's going to be one sum. And then step 3 is to identify the recurrence relation. Right? Identify the recurrence relation. And finally, step 4, solve the recurrence relation to find the coefficients. All right, so that's the general process that we're going to use to solve these power series, to find these power series solutions to our differential equations. And let's now do an example where we see how this all works. So we work it out. I'm going to give you guys some time to work it out on your own, and then we'll come together and we'll do it together. But here's our example that we'd like to solve. So for this one, this is like I was saying before, I'd like to find at least the first 6 terms of the power series solution to the initial value problem. And so I'll write it down, and then we'll talk a little bit about how to solve the initial value problem, and then we'll do it together. But the differential equation is 1 minus x y double prime plus xy prime plus, minus y. So minus y equals 0. The initial conditions are y of 0 equals minus 3 and y prime of 0 equals 2. And so the idea here is that we want to do exactly what we did before. We have a slightly more complicated equation, right? But the point that we want to center around is if you're given an initial value problem, it's always going to be the initial x value. So for this one, it's 0 again, right? So, but we always want to center around the initial condition, the initial point, right? So we want to center this around x naught equals 0 because of this, right? And then do the same process, but at the end you can use the initial conditions to solve for a0 and a1. So use the initial conditions, right, to find or solve for a0 and a1. So I'm going to give you guys a few minutes to work on that. Pause the video, do the best you can, and then when you come back, we'll work it out together. All right, let's see how this one goes. So remember the process here is to write out the power series and plug them into the differential equation and then try to combine it into one. So let's write out our power series again. We'll go with the standard version. We're centering at 0 again, so this is going to be a sub n x to the n. Y prime is going to be the sum and goes from 1 to infinity, n a sub n x to the n minus 1. And y double prime is going to be the sum and starts at 2 to infinity, n times n minus 1, a sub n, x to the n minus 2. These have to be plugged into the differential equation. So I'm going to actually distribute this term out, the 1 minus x, so that this is going to be, I'll rewrite the whole thing here, but y double prime minus x times y double prime plus xy prime minus y, and then I'll write out the power series version here. So this is n from 2 to infinity, n times n minus 1, a sub n, x to the n minus 2, minus x times the sum, n from 2 to infinity, n minus 1, a sub n, x to the n minus 2, plus x times the sum, n goes from 1 to infinity, n a sub n, x to the n minus 1, and then finally minus just the sum, n from 0 to infinity, a sub n, x to the n. This is all supposed to equal 0, right? So now what we need to do is combine these into a single sum. There's a couple things that we can do. First of all, these x's that are out front can get multiplied in. All right, and it's going to have different effects on each of these two. So I'm going to do that first, and then we'll talk about, or we'll consider any shifting of indices that needs to be done at that point. But this is the same. This one, when it goes in, everything else stays the same, but it's going to add 1 to the power, right? So this will now be n minus 1, a sub n, x to the n minus 1, right? This one, when it goes in, that's going to make that x to the n. So sum n goes from 1 to infinity, n a sub n, x to the n. And then this one is good to go, right? Again, this is 0. All right, and so the next step is going to be to shift the indices, so that each of the x's are of the same power, right? So this one needs to be shifted 2, this one has to be shifted 1. Those are the only two that we have to shift. Notice the shifts are different for each of those, right? So this one's going to be shifted by 1, this one's going to be shifted by 2. Remember how this works. The ends in the sum and go up 1, and therefore the index down below in the sum goes down 1, right? So let's write this out then. The first one's going to be sum. N goes from 0 to infinity. N plus 2. This one's moving by 2, right? N plus 1. A sub n plus 2. X to the n. So that one's good. This one's moving by 1. So this sum will start at n equals 1. Then this will be n plus 1 times n. A sub n plus 1. X to the n. And these two are left alone, right? Notice that these two start at 1, so we're going to have to deal with that in the next step here. n a sub n x to the n. Now I'm just copying, right? This one starts at 0, though. A sub n x to the n, again, still equal to 0. Now that I have the powers of x the same, I want to combine this into a single sum if possible, right? And so what I need to be careful of now is that these two, let me use a different color, these two start at 1, where the others start at 0, right? Now I can't add terms to these that don't exist, but I can take away the first term from each of the two that start at 0. So what I'm going to do is take out the first term of each of these that start at 0. So take out the first term of this one and the first term of this one. Be careful about this minus sign. And then everything else is going to be able to be combined into a single sum that starts at n equals 1 after I take those out, right? So the first term, the 0 term from this one, is going to be 2 times 1 times a sub 2 x to the 0, right? So 2 times 1 times a sub 2, I'm going to write it, x to the 0, that's obviously 1, right? This one is going to just be a sub 0 x to the 0. So minus a sub 0 x to the 0. Those are just constants, right? And then the rest of this, once we've taken those two out, then what's left, right? Once we've taken that single term each from each one of these, what's left is going to start at 1 then, right? So now I can combine everything else into a single sum, starting at n equals 1. And then just like we did before, take all the coefficients, group them together, and factor this x sub n, or x to the power n, off to the right, okay? So here's what we're left with. N plus 2 times n plus 1, a sub n plus 2, minus, be careful of the signs, n plus 1 times n, a sub n plus 1, plus n times a sub n, minus a sub n, okay? And then all times x to the n, that's all got to equal 0. All right? Now again, I've talked about this, but now what we can do is we can just ignore these powers of x, right? Right? Ignore these because those x to the 0, because those are just 1s, right? And then what we need to do is set all of these things equal to 0. So this is going to be part of our recurrence relation. So this one tells us that 2 a sub 2 minus a sub 0, that should be 0. Because if that's anything that's non-zero, then we're not going to get 0 on this side, right? So that's got to be 0. That's part of our recurrence relation. And then the rest of this is going to give us the rest of our recurrence relation. So this is just true for those specific terms, right? The rest of this, though, we can write, this one's going to be n plus 2 times n plus 1, a sub n plus 2, minus n plus 1 times n times a sub n plus 1, plus, I'm going to write this as n minus 1, because we can factor this, right? A sub n, those are the only terms with a sub n's, and this whole thing has to equal 0. This is true now for n equals 1, 2, 3, etc., right? Starting at 1. So n greater than or equal to 1. It's a better way to say that. Right? So in other words, this recurrence relation doesn't apply for n equals 0, but we have our n equals 0 term over here, right? So altogether, these are our recurrence relations now. To get taken as a whole, our recurrence relation comes in two parts, right? It comes in the equation for n equals 0, and then the rest of it for all the rest of the n, okay? So now we just have to solve these recurrence relations. And so the first one, then we can just rearrange this, right? And a2 is going to be equal to 1/2 a0. That comes from this. Now the rest of this, a0 and a1 are going to be free again. They always are, right? But now the rest of this one can be rearranged and solved for a sub n plus 2. So a sub n plus 2 is going to equal 1 over n plus 2 times n plus 1 times, this all moves over, and this will be n plus 1 times n, a sub n plus 1, minus n minus 1, a sub n. And again, this is true for n greater than or equal to 1. All right? Now, if we want to do this in the simple-minded way that I did the previous one, we can swap out our n plus 2 for k, so we can make our list. You don't have to do this, but again, I like to do this because I like to see the proper index on the term that I'm working with, and then you can adjust from there, right? So if you decide to do this, then this one will become a sub k is equal to 1 over k times k minus 1, right, times k minus 1 times k minus 2, right, a sub k minus 1, so previous one, minus, this one's going to be k minus 3, right? So remember how this works. N is equal to k minus 2, so you put this in here, this will be k minus 3, a sub k minus 2. And now this is true for k bigger than or equal to 3, right? So that's going to be true for k bigger than or equal to 3. Now, let's go back up. We were asked to find the first 6 terms. So we need A1, A0 through A5, I guess, if we're going to do it that way, right? So let's write them out. So A sub 0 is free. A sub 1 is free. And then our recurrence relation kicks in for the rest of them, right? By the way, I'm going to put a box around this because this is the formula that I'm going to use to solve the rest of these. All right, but obviously we need this one too. So a sub 2 is equal to 1/2 a sub 0. Now we've got it in terms of one of the free ones. These should be the only two that are free. And a sub 3, we now use this formula, right? So a sub 3 is going to be 1 over 3 times 2 times, this is going to be, what, 2 times 1, right? 2 times 1 times a sub 2 minus 0 times a sub 0, a sub 1, sorry. All right, so this one, again, we're just trying to find the first few terms. So this one's going to be 1/3 a sub 2, but a sub 2 is in terms of a sub 0, right? So this one's going to be 1/6 then a sub 0. All right, then we go down to the next one. So a sub 4. We need 6 terms in the power series, so that's going to be, it starts at 0, so we need through a sub 5, right? This one's going to now be a sub 4 is going to be 1 over 4 times 3 times 3 times 2 times a sub 3, right? Minus, this is going to be 1 times a sub 2. All right, we put this all together. This one's going to be now what? The 3's cancel, 2's cancel. So this is going to be 1/2 a sub 3 minus 1/12 a sub 2. And we have formulas for both of those. They're both in terms of a0, right? So this one's now going to become a sub 3 is this one. So this will be 1/12 a sub 0 minus 1/24 a sub 0, which is, of course, 1/24 a sub 0. So notice, just based on the way these are going, these are all going to be in terms of a sub 0 except for this one, is a sub 1. Okay, so a5, then this is the last one that we need for this example. This is 1 over 5 times 4, and then it's going to be 4 times 3 times a sub 4 minus 2 times a sub 3. All right, and so again, this is now going to, if you combine this is going to be 3/5 a sub 4 minus 1/10 a sub 3. 3/5 a sub 4. So 3/5 times 1/24. I'll just write it all out. 3/5 times 1/24. So that's going to be 1/40th, right? A sub 0 minus 1/10 a sub 3. So that's 1 over 60 a0. And yeah, this is cancels to be 8, right? So this is 1 over 40 minus 1 over 60 a sub 0. And that is going to be what? That's going to be, so 6 minus 4 is 2 over 240, so 1 over 120, right? So this one's going to be 1 over 120 a0. And so now we can write out our power series solution. At least the first, like we said, the first 6 terms, right? So what we have then is that our y is going to be equal to a0, right? Remember, this is centered at x not equals 0. So a0 plus a1 times x plus a0, 1/2 a0. So this is a2 now, right? So now we're plugging in the two terms, so plus 1/2 a0 x squared plus 1/6 a0 x cubed plus, this one's 1/24 a0 x to the 4th, and then plus 1 over 120 a0 x to the 5th. And then obviously the solution continues, right? But this is what we have so far. And so we can rewrite our solution now, and we can kind of factor it into terms, right? So we can say we have our a0 times this function, 1 plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4th plus 1/120 x to the 5th. And you might be able to recognize a pattern here. And then plus a1 times x, right? And so remember, we have initial values for this. By the way, in a minute, I'm going to finish this up because the instructions said just find the first few terms, but we're going to be able to, we're going to know what that, we're going to be able to write down exactly what this function is. Okay, so anyway, yeah, so these, we have initial values to help us determine the a0 and the a1. So if we go back up here, remember a0 is always y of 0, so this is a0, and a1 is y prime of 0, because we're centering at the point, right? So you can work this out, but a0 is -3 and a1 is 2, and so we just plug those numbers in. So the particular solution then is -3 times this function. All right. And then plus 2 times that function, which is just x, right? I did something very bad. I did not include the ellipsis here. It's very important, right? This is a power series, so this continues on forever. It's not a solution if you cut it off. So the solution has to include everything, right? All right, so this is the power series solution, the first 6 terms that we were asked for. But then we might notice, right, that this is actually something that we can say exactly what this is, right? So this function, you'll notice these terms down below, these are factorials. So this is 2 factorial, 3 factorial, 4 factorial, 5 factorial, right? So these are factorials. And so this whole thing looks like it's missing a term right here, right? It's missing the x term. It's missing just x. So this one looks like the sum, n goes from 0 to infinity, of 1 over n factorial x to the n, but then it looks like that take away the x to the 1 term, right? So take away x. And I hope you notice that this one is our function e to the x, right? That's e to the x. So actually this solution can be written as y equals -3 times e to the x minus x, because it's this whole series, take away that term, right? Plus 2x. And then we can rearrange this, right? So that y is then going to be -3 e to the x plus 3x plus 2x, so plus 5x. And so based on this power series method, here's the first 6 terms of the power series solution, but here is another way to represent this function. So you can check that and go back and verify that that function indeed solves the differential equation, and that the initial values are satisfied as well. Okay, so but there's an example of how you can solve an initial value problem using the power series method. So what we would like to do next then is take a little bit different point of view here. So for this one, for the next step here of what we'd like to do, I'd like to just assume that we have a solution. All right, so for this one, let's suppose that we have a power series solution, phi of x, and again, power series, so sum n goes from 0 to infinity, a sub n, x minus x naught to the power n. So this is a power series centered at x naught. Assume that this is a solution of our differential equation star. Remember, that was from the very beginning, the second order linear homogeneous differential equation. And assume that the solution converges on an interval with a positive radius of convergence. So suppose that this converges on this interval, x minus x naught less than rho, for some positive value of rho. Okay? Now, further, let's suppose that x naught is an ordinary point. All right, so we're still dealing with ordinary points, but let's say it specifically here. So then what this means then, remember, we said that this is where I'm going to add a few details to what we mean by ordinary point, okay? But this means, recall, that this means that p of x naught is not equal to 0, right? So our differential equation, which was given as p of x times y double prime plus q of x times y prime plus r of x times y equals 0. This one can be transformed near x naught. So these, by the way, I probably should have said some more about the coefficient functions, but let's assume that these functions, so if p is continuous at x naught, then actually what this means is that p of x is not equal to 0 in a small neighborhood. So in a small, at least a small, maybe large, but in a neighborhood about this point x naught. And so what that means is that we can divide through this equation and we can write, so we can divide by p of x near this point x naught, and we can get this new differential equation that's in the form y double prime plus little p of x y prime plus little q of x times y equals 0. And so we're going to assume then, and it works out, but we're not going to go through all the details. When I say assume, I mean we're not going to go through all the details here. But where these functions, p of x equals our function, our old functions, right? So capital Q of x divided by capital P of x, and little q of x equals capital R of x over capital P of x. So where these functions, we're going to say, have convergent power series centered, so convergent power series representations centered at x naught. Okay, so if we know that we have a power series solution, that's part of the assumption that we've made here, right? That we have a power series solution that's convergent on this interval, then this must be true. And again, I'm not going to go through all the details in this lecture about why that must be true, but we can just take it for granted. We can say, okay, this is going to be true. So we can write our differential equation in this form, y double prime plus little p of x y prime plus little q of x y equals 0. Where these two functions, p and q, are themselves, they're not necessarily power series, but they have convergent power series representations themselves. Okay, so that's our main assumption here. Now, once we know this, once we believe this, then what we can do is we can rearrange to solve for our solution. So based on, let's first look at our solution here. So we have our phi of x equal to the sum, n goes from 0 to infinity, a sub n, x minus x naught to the power n. If we plug in x naught, what are we going to get? Well, let's first write out the terms of this, right? So this power series as a expansion here, this would look like a sub 0 plus a1 times x minus x naught plus a2 x minus x naught squared plus a3, etc. x minus x naught cubed, right? Etc. All right, now if you plug in x naught to this power series, what are you going to get? Well, you're going to get a naught plus, when you plug in x naught for the x in all the other terms, you're going to get zeros, right? And so this is just going to be a sub 0. So phi of x naught is a naught, and you know this is always going to be true for the center point. The next thing that you plug in, phi prime. Well, let's write down phi prime of x first. Phi prime of x is going to be, take the derivatives. This one's gone. We talked about this earlier, right? So what's it going to be? It's going to leave a1 plus, and then take the derivatives of the rest, right? 2a2 x minus x naught plus 3a3 x minus x naught squared, etc. And again, you plug in your x naught to phi prime, and you're going to be left with just a1. All right, now the second derivative gets a little bit different here. So what's going to be different about it? Well, you take the next derivative, what are you left with? You're not left with a2, you're left with 2a2 plus, and then the next term you get is 3 times 2 times a3, x minus x naught, etc. And when you plug into this one, phi double prime of x naught is going to be 2a2. And if you continue this process, what you'll find is that the mth derivative at x naught is always going to be equal to m factorial times a sub m. All right, and you can work that out just by noticing this, right? Do it again, you're going to get 3 times 2 times 1 times a3. Next one, 4 times 3 times 2 times 1, a4. So you'll see that this is a formula that's always going to be true. Okay, so this relates our functions, so the coefficients of our power series to the derivatives of our solution function, right? At the center point. All right, now here's what we want to do. By the way, we know that a0 and a1 are kind of the free ones, right? Well, if we go back to our differential equation, the form that we have it here, 2-star, right? 2-star form of the equation, we can solve this for what will be phi double prime, right? So if we go back to our equation, plugging into our equation 2-star, we have, right, that phi double prime plus little p of x phi prime plus little q of x phi must be 0. And so we can solve this and we can write, all right, phi double prime of x in general is equal to negative p of x times phi prime of x minus q of x times phi of x. And now if we plug in our point, x naught, then look what we get. So I'm going to write this, I'm going to do this in 2 steps for this one, and then we'll kind of simplify. But p of x naught, so that's the value of that coefficient function at the center point, times phi prime of x naught minus q of x naught times phi of x naught. And then we can say, all right, well, phi double prime at x naught, on one hand, we know it's equal to 2a2, right? We just worked that out. On the other hand, it's equal to this. Well, what is this? This is going to be, I'm going to write this as negative p sub 0, so that's just p of x naught, times phi prime at x naught, that's a1, right? That's a1, minus q naught, so that's the value of q at x naught, q naught, times phi at x naught, which is a0. All right, and then solving for this, what we get is that a2 is always going to be negative 1/2 times, so moving it over and factoring out this 1/2, times p naught of a1 plus, or times a1, q naught times a0. So in other words, the coefficient a2 will always depend on a0 and a1 and on the coefficient functions p0 and q, p and q at the point, right, at x naught, and it's given by this formula. And we can continue this on and on and on to find, just repeat this process over and over again to find formulas for all of the a sub n. All right, but each one depends on the previous one, obviously. So continuing this process, here's what you'll get. So remember, we have phi double prime at x is equal to this formula, right? P of x times q, phi prime, negative p of x times phi prime of x minus q of x times phi of x. And then if you take the derivative, you'll get a formula for phi triple prime, which is going to be a whole bunch of product rules, not a whole bunch, just 2. But it's the derivative of all this, right? So negative p of x, phi prime of x, minus q of x, phi of x. All right, and so a little more work. I'm just going to write down what we get here. But if you take the derivative, plug in x naught, plug in all your previous, everything you know previously, then what you'll get is the following. So you'll get phi triple prime at x naught is equal to, on one hand, it's 3 factorial a sub 3, right? On the other hand, it's negative 2 factorial times p naught times a sub 2 minus p naught prime, so that's p prime at x naught, plus q naught times a1 minus q naught prime. So again, that's q prime evaluated at x naught. So at the point times a0. And then we have a value for this, right? A2 is this. A2 is this, right? And so what we end up with is then 6a3 is equal to the negative 2 factorial and the negative 1/2 cancel. And so we'll get p0 times p0a1 plus q0 a0 minus p0 prime plus q0 a1 minus q0 prime a0. And you can rearrange all of this then to have a formula for a sub 3 in terms of all this, right? So in terms of this, what are we going to get? We're going to get, so times our, I'll write it like this. So we'll have two terms. So our a0 term is going to be p0 times q0 minus p0 prime minus q0 prime. Nope, sorry. It's just minus q0 prime. So I'm doing a0, right? So the a0 term is just going to be this portion, this times this, minus this, right? So this is minus q0 prime, that's times a0, plus this one's going to be p naught squared, right? p0 times p0 minus p0 prime minus q0 times a1. Okay, so that's enough, right? So but that is a formula for a3. It depends on a0 and a1, and then it depends on the coefficient functions evaluated at the center point and their derivatives now, right? And so as you go up further, as you go further in this process, a4 is going to depend on second derivatives, and it's going to get more complicated, right? It's going to get more complicated as you go, and more tedious as you go. But the point is that you can always do this process, right? And you can find formulas for your coefficients that depend on the free ones, the free coefficients, a0 and a1, and then only on those coefficient functions, p and q. And that's the key here, right? So if we write this down, then what this whole derivation proves is that a sub n will depend on the first two coefficients, a1 and a0. That's not really news. We've kind of seen that from our other studies, right? And it depends on the values of p, q, and their derivatives, right? And their derivatives at the center point, x naught. All right, so a sub n depends on these two free variables, which they're free, so that's not a major deal. But really, what the key here is that it depends on p and q's derivatives, right? Remember, p and q we assumed have power series representations at the center point, right? And so because of this, we're going to arrive at the following theorem. And again, this is not really a proof, but this is a derivation to at least justify the following theorem. And this following theorem is very powerful. It's kind of like a fundamental existence and uniqueness theorem for power series. So it says the following. We'll write it out, and then we'll just do one simple example. And then this long lecture will be over. But here's the theorem, though. It says if x naught is an ordinary point, if this is an ordinary point of the differential equation star, which I'll rewrite because we have a theorem here. So this is p of x times y double prime plus q of x y prime plus r of x y equals 0. And so ordinary point here is going to encapsulate everything I'm about to write next, but I'm going to write it anyway. So, and if little p of x equals capital Q of x divided by capital P of x, and little q of x equals capital R divided by capital P, if these functions have convergent power series representations at x naught, then the general solution of equation star, so the general solution of equation star is given in the following form. So it's a power series for one. It can be written as a power series, but y is equal to the sum n 0 to infinity a sub n x minus x naught to the power n. So this is the existence part, right? And this can be broken up into a sub 0 times y1 plus a sub 1 times y2, where in this scenario the a0 and a1 are arbitrary constants. All right. And y1 and y2 are convergent power series centered at x0. So this is basically everything that we've just studied in this lecture is wrapped up in this theorem, and this is the existence theorem that says that as long as our coefficient functions are nice enough, right? We have an ordinary point, our coefficient functions are nice enough, then everything that we've talked about in this lecture is not going to be a waste of our time. We can solve the recurrence relation if we do it that way, or we can use another method, right, to do it a different way, to find the power series representations of our solutions. And then now there's two more parts of this theorem that are kind of the uniqueness part of the FEUT. So that's the existence. We can find a solution. The next part of it says that actually this solution is unique, right? And so it says the following: the functions y1 and y2 form a fundamental solution set. So that means their Wronskian is non-zero. So they form a fundamental. So there's your uniqueness, right? They form a fundamental solution set. So again, that means that the Wronskian at the ordinary point is not zero. Right? It's non-zero. And then finally, the radius of convergence of y1 and y2 each is at least as large. So this is at least as large as the radii of P and Q. So this is a consequence of our differential equation being linear, that we can actually determine the domain of the solution without solving it, because, well, at least we can determine a lower bound on the domain, right? A lower approximation of the domain. So that's it. That's the fundamental existence and uniqueness theorem for these power series solutions at an ordinary point for a linear, homogeneous, second-order differential equation. Okay, so this is another version of our FEUT PS, we'll call it, power series fundamental existence and uniqueness theorem. So now let's use it to answer one question. So let's suppose that we have the following differential equation: 1 plus x squared y double prime minus 2x y prime plus alpha times alpha plus 1 y equals 0. So homogeneous, second order, linear differential equation, where here alpha is just some real number, some parameter. All right. I want to know what is a lower bound for the solutions radius of convergence about two different starting points. So x0 equals 0 and then x0 equals 1. All right, so the way that we do this is we have to find the functions little p and little q. So we need to modify our equation, right? By the way, those are both ordinary points because this term right here is not 0 for either of those, right? When you plug in, this is always positive actually, so every point is ordinary in that sense, that the p of x0 is going to be non-zero. So we can divide through, and our differential equation will now look like y double prime minus 2x over 1 plus x squared, y prime, plus alpha times alpha plus 1 over 1 plus x squared, y equals 0. And so that means that these are our coefficient functions, right? So this is our function p of x, and this one is our function q of x. All right, and both of these are going to have convergent power series, so they're rational functions, right? So they're going to have convergent power series away from any points that make them undefined in the denominator. So one way that we can do this, that we can solve and find a bound on the radius of convergence, is to use a little geometry. So the quote-unquote, the points where P and Q are not continuous, right? For each of these two functions will be where 1 plus x squared is equal to 0. Obviously, there's no real numbers that are going to satisfy that. We just talked about that, right? But complex numbers have an effect on radius of convergence of power series. So maybe you remember this from Calculus 2. But one nice and interesting way to kind of find the radius of convergence of a power series is to consider you've got your real number line, which is the domain of these functions, but then if you include the imaginary number line as like the second dimension of two-dimensional space, then you can plot the quote-unquote bad points, the problem points of this equation, right? So this obviously to solve is going to have two solutions. X is equal to plus or minus I. Those are the points that make this 0, right? And remember, in the complex plane, I and minus I lie 1 unit away from the origin on the complex, the imaginary axis, I should say, right? So now let's think about where are our center points. Our center points were x naught equals 0 and x naught equals 1, right? These are going to have different radii of convergence. So the way this works then is that from 0, we can go in the x direction only as far, we're only guaranteed to be allowed to go as far in the x direction as we can go in the y direction, as far as, x and y coordinates of complex space. So we can only go 1 unit then, right? So that's supposed to be a circle. Use your imagination. But the point is that's a circle, and so at x naught, the minimum radius of convergence, though, is going to be 1, because x equals 0 is 1 unit away from these points that make the denominators of our coefficient functions equal to 0. All right? So for x naught equals 0, the minimum radius is going to be 1, right? So the radius is greater than or equal to 1. All right, what about from 1? Well, for this one, the radius is going to be the distance to the shortest distance to one of these. These are equidistant, right? And so the circle that is centered at that center point 1, we're going to be able to go in the x direction only as far as we can go in the y direction. So the interval here is going to be like this, right? Well, how long is this term? Well, this is a isosceles right triangle. That's going to be the length of square root 2, right? 1 squared plus 1 squared is 2. All right, so from x naught equals 1, the radius is greater than or equal to square root 2. Okay, so notice you get a lot more room, but you have lost some area over here, right? So where you choose your center point is going to determine, sometimes you don't get to choose it, right? Sometimes the initial condition gives that to you, but the center point together with the functions p and q, those are going to determine the minimum radius of convergence of your solution, and you are guaranteed by that fundamental existence and uniqueness theorem to have your power series solution converge within that radius, right? Maybe more, but at least within that radius. So in this case, it's square root 2 from the center point x equals 1. It's just 1 from the center point x equals 0. Okay, so this is an introduction to power series solutions of differential equations. In the next lecture, we'll talk about what to do with singular points. But I'm going to leave this one here, and I'll talk to you guys in the next one.